Special course in mathematics, lecture 4, topology. We start today from the basic operations with sets. Recall that given a set X and an element A, we denote in this way the logical statement that A is an element in X, and in this way we denote the logical statement that A is not an element in X. And given two sets X and Y, we can define the following operations. We can define the union of X and Y as the set of all elements A which belong either to the set X or to the set Y. And we can define the intersection of X and Y as the set consisting of all elements A which belong both to X and to Y. Next, we can define the difference between X and Y, X set minus Y, as the set of all elements in X which do not belong to Y. And we can also define the symmetric difference X delta Y as the union between X minus Y and Y minus X. Also, recall that given two sets X and Y, we denote in this way the statement that each element of X is an element of Y. In this case, the set X is called the subset of Y. And finally, given a subset X of Y, the complement of X in Y, which is usually denoted by X overlined, is defined as a difference between X and Y. Next, let us talk about the Boolean of a set. Definition: given a set X, the set of all subsets of X is called the Boolean of X. It is usually denoted by b of x or 2 to the power x. For example, if the set X consists of two elements 1 and 2, then its Boolean consists of four elements: the empty set, the singleton Y, the singleton 2, and the set X, the set consisting of the elements 1 and 2. If X is a finite set consisting of exactly k elements, then the cardinality of the Boolean of X is equal to 2 to the power k. Indeed, subsets of X are in a natural bijection with functions from X to the set with two elements 0 and 1, where, given a subset Y of X, the corresponding function f takes value 1 exactly at the elements of Y. To enumerate such functions, if we have a set with k elements, we know that the value of f at each element can be chosen in two different ways, and then we apply the multiplication rule of combinatorics. And, of course, this explains the notation 2 to the power x. The cardinality of the Boolean is 2 to the power the cardinality of x. Now let us talk about some basic properties of set operations. Note that the union, intersection, and the set difference are binary operations on the Boolean, and the complement is a unary operation on the Boolean. Property 1. For a set X, the tuple consisting of the Boolean of X, the binary operation of taking the union, and the empty set is a commutative monoid. Property 2. For a set X, the tuple consisting of the Boolean of X, the operation given by the intersection of subsets, and the set X as a specific element is also a commutative monoid. So this essentially says that the union and the intersection are associative operations, and the empty set is the identity element for the union, and the whole set X is the identity element for the intersection. So that's clear. Now here a more tricky property 3. For any set X, the tuple consisting of the Boolean of X, the symmetric difference delta, and the empty set is a commutative group. So the symmetric difference delta, it is not only associative, which is now quite non-trivial, but there are also inverses with respect to delta. And to see that there are inverses where the identity element is the empty set, we know that the symmetric difference of any set with itself is the empty set by definition. And also, if the symmetric difference between two subsets is the empty set, then these two subsets must coincide. So using this, it is very easy to see that property 3 holds. Next, let us talk a little bit about the properties of the complement, of taking the complement inside the Boolean. Assume that U is a big set, which we call the universe, and that X and Y are two subsets of U. And on this slide, by complement, we will always mean the complement with respect to U. So now property 4, the complement of the union of two sets, so the complement of the union of X and Y, is equal to the intersection of the complements of X and Y. Proof: the element X belongs to the complement of the union of X and Y if and only if X doesn't belong to X and X doesn't belong to Y. But of course, this means exactly that X belongs to the intersection of the complements of X and Y. And this completes the proof. Similarly, we have property 5, which says that the complement to the intersection of X and Y is equal to the union of the complements of X and Y. So this is proved similarly to property 4. So here is property 6. Taking the complement twice gives us the original set X back. And a very trivial property 7, the complement of the empty set is the whole set U, and the complement of U is the empty set. Okay, so now, after recalling all the set operations, we can define the notion of a topological space. Definition: a topological space is a tuple consisting of two things. First of all, a set U, and then a subset curly T in the Boolean of U. So a collection of subsets of U. And this tuple should satisfy the following axioms. First of all, both the empty set and the whole U should belong to T. Next, T should be closed under taking finite intersections. That is, if we have two elements X and Y in T, then their intersection, X intersection with Y, should belong to T. And finally, T should be closed under taking arbitrary unions. That is, if we have a collection of elements in T, xi, indexed by some index I, which belongs to some set I, then the union of all xi's should belong to T. And the terminology, this T is called a topology on U, and elements of T are usually called open sets. Here are some examples. Example 1. For any set U, we can take as open sets on U just the empty set and U itself. And in this way, we get a topology on U, which is usually called the trivial topology. All axioms are obviously satisfied, so the empty set belongs to it, the U belongs to it. So this is closed with respect to finite intersections and arbitrary unions. So all axioms are trivially satisfied. Example 2. For any set U, we can take the topology on U, which consists of all subsets of U. Then we get a topological space. This is usually called the discrete topology, and all axioms are trivially satisfied, because the topology contains all the subsets of U. And the third example, a less trivial example, for any set U, we can define the topology T on U as follows. We declare that a subset X of U belongs to T if and only if X is empty or its complement has finitely many elements. Then we get a topological space, which is usually called the space with cofinite topology on U. And again, all axioms are satisfied. So by definition, the empty set and U belong to this topology. This is closed with respect to finite intersections, because when you take finite intersections, for the complement you take finite unions, and finite unions of finite sets are finite. And this, of course, is closed under arbitrary unions, because when we take arbitrary unions, then for the complement we should take arbitrary intersections. And of course, arbitrary intersections of finite sets are finite. Great. Now let us talk about closed sets. Let U be a topological space. Definition: a set X in U is called closed if and only if its complement is open. Here are some properties of closed sets. Both the empty set and U are closed. Finite unions of closed sets are closed. And arbitrary intersections of closed sets are closed. For example, in the trivial topology, it is exactly the empty set and the whole of U which are closed. In the discrete topology, all sets are closed. And in the cofinite topology, it is exactly the finite subsets of U which are closed. And of course the U itself by definition. Great. This allows us to give an alternative definition of a topological space using closed sets. So a topological space is a tuple which consists of some set U and a collection C of subsets in U satisfying the following conditions. Both the empty set and the whole of U belong to this collection C. C is closed under taking finite unions. So if we have two elements in C, their union is in C. And C is closed under taking arbitrary intersections. That is, given a collection xi of elements in C, the intersection of all these xi's belongs to C. And all elements of this collection C are called closed sets. Let us note that some people also call this C a topology on U, and this is very confusing. One should, to the very least, say that C is a collection of closed sets. But of course we can define a topological space using either open sets and then axioms for the open sets, or closed sets, and here are the axioms for the closed sets. And the connection between the two definitions is given by taking the complement. So we can define a topology using open sets, and then the complement of an open set is closed, which means that we can alternatively define a topology by prescribing what the closed sets are. One just should remember that the axioms for open and for closed sets are dual to each other. So for open sets, we have arbitrary unions and finite intersections, and for closed sets, we have arbitrary intersections and finite unions. Great. Next, let us discuss the notion of the basis of topology. Let U be a topological space with some topology Carly T. Definition: a subset Carly B of Carly T is called the basis of T, provided that every element in T is the union of some elements in B. Note, by convention, the empty union equals the empty set, so the empty set will always be in the union of elements in B. And terminology, the elements of such basis B are usually called the basic open sets. For example, we can always take as B the whole of T, and then everything is clearly satisfied. A second example, if you look at the discrete topology, this is when T contains all subsets of U, then we can take as a basis of this topology the singletons. Any set is a union of singletons. So this works. A less trivial example, if you consider the Euclidean topology on R to the power n, then it is the open balls which form a basis of this topology. So our aim today is to prove Euclid's theorem that there are infinitely many prime numbers using topology. So in order to do this, we will define a very strange topology on the set of all integers. So let us define this strange topology, we denote it by T, on the set of all integers. So we define the topology T as follows. A subset X in T is open if and only if it is a union of some sets of the form a plus bi, where I belongs to z, where a and b are integers and b is non-zero. So in reality, this means that these are cosets of the additive group Z modulo the subgroup BZ. So we define our topology T by saying that these subsets form a basis of T. The subsets of the form A plus BI, where I is an integer, they form a basis of T. That's our definition. Then, of course, from the definition, it is clear that this topology contains both the empty set, that's the empty union, and the set of all integers, because we can take a is equal to b is equal to 1, and then this set gives us the set of all integers. So the first condition for the topology is satisfied, and then this by definition is closed with respect to taking arbitrary unions. So this condition is also satisfied. So let us check that this definition gives us something which is closed with respect to finite intersections. And in order to prove this, in order to prove that T is closed with respect to taking finite intersections, it is enough to check that the intersection of two subsets in our basis is either empty or is a subset of the form as in our basis. So the intersection of a plus bi where I is in z with c plus di where I is in z is either empty or of the form x plus yi where I is in z. So let's assume that the intersection is not empty. So there is an integer r, which we can write both as a plus bi and as c plus d j. Recall that both b and d are non-zero by definition. And let us define the integer m as the least common multiple of b and d. Then the intersection q of our two sets, a plus bi for all I and z and c plus di for all I and z, is equal to the set r plus mi where I is in z. R is our common integer here, and m is the least common multiple of b and d. Indeed, of course, the fact that this set r plus mi belongs to q, this is clear. Of course, r belongs to q, and m is a least common multiple. It is divisible both by b and d. So r plus mi, of course, has the form r plus something times b, and it also has the form r plus something times d. So that's clear. In order to prove the reverse inclusion, let us assume that we have some number r prime, which has the form a plus bi prime and c plus dj prime. But then we can subtract r from r prime, and then a cancel, and we get b times I prime minus I. So b divides the difference between r prime and r. And similarly, d divides the difference between r prime and r. And this means that m must divide this difference. And so this means that our q is a subset of this set, of the set of the form r plus mi where I is in z. And this completes our proof. So the intersection of two elements in the basis is either empty or an element in the basis, and so the intersection between two unions, that's a union of the intersections, it's again a union of subsets of our form. Now let us make some observations. First of all non-empty sets in our topology are infinite. Indeed, if we have a non-empty union, each set in this union is infinite. So all basic open sets are infinite by definition, so all non-empty sets in our topology are infinite. The second observation, all basic open sets are closed. Indeed, so we need to prove that each basic open set, a plus bi, where I is in z, is closed. So this means that its complement should be open. Let us now write down a complete list of representatives of cosets in Z modulo Z sub B. So we start with our A, that's our representative A1, then we have A2, A3, and so on, AB. Great. But then the complement to our set A plus BI is the union of AS plus BI, where I is in that, where S is 2, 3, and so on B. And that's a finite union, and each of the elements of the union is open. So this finite union is open, and so the complement to it is closed. And that's the set we started with. So all our basic sets are both open and closed. Great. Now we are in the position to prove Euclid's theorem. Assume that we have only finitely many prime numbers, p1, p2, and so on, pk. Consider the following basic open sets in our topology. ps times I, where I is in z. So this is of the form 0 plus ps times I. We have finitely many open sets, and each of them is closed. So this is a finite union of closed sets, so it is closed. Hence, its complement must be open. But the complement to this set, so this is the set of all integers which are divisible by at least one prime number. There are only two integers which do not have prime divisors. These are 1 and -1. So the complement to this closed set is the set which consists of two elements, 1 and -1. So the set of 1 and -1 should be open. But that's a contradiction. We saw that all open sets in this topology are infinite. And this contradiction completes the proof of Euclid's theorem. Some extra problems and questions at the end. Problem question 1. Prove with all details that the Boolean of x with respect to union and with the empty set is a commutative monoid. Problem question 2. Prove with all details that the Boolean of x with respect to the symmetric difference and the empty set is a commutative group. Problem question 3. Prove with all details that the complement to the intersection is the union of the complements. Problem question 4. Let B be a collection of subsets of U which contains the empty set, and let us assume that B is closed under finite intersections. Shows that the set of all unions of elements in B is a topology on U, and that B is a basis of that topology. Problem question 5. What happens with our argument in the proof of Euclid's theorem if we know that there are infinitely many prime numbers? So what happens with the several arguments in the proof? Thank you very much, and see you next time.